In today's training, I'll be presenting the Libero design flow presentation, and I will also walk you through the Libero tools. Here is the agenda for today's training. So Libero SoC is basically the Microchip FPGA's EDA software, which is used to design the FPGA designs from the design entry to the programming and debug. 12.x software supports the PolarFire families, SmartFusion2 family, Igloo 2 family, and RTG4 family. So in our designs, I'll be targeting the PolarFire family. So Libero is comprehensive because using a single tool, you can actually create your design from the entry to the programming and debug. It is easy to learn because it's intuitive and it's a GUI based wizard. If you are not comfortable with the tickle scripts, you can actually use the GUI wizard to create your designs. It is easy to adopt because it's a single click flow from synthesis to programming, and it supports all the collaterals that are required for the users. So here are the Libero editions. So basically we have two Libero editions. One is the IDE, the other one is the Libero SoC. The Libero IDE is an old and legacy software which is used for the antifuse and old RT families. There are no enhancements for the IDE. We actually do bug fixes with the service packs if there are any bug fixes required for the IDE software. On the other side, the Libero SoC edition has two sub branches. One is the 11.9 and its service packs. So using this 11.9 and older versions of Libero SoC, it supports the G3 families. So G3 means the ProASIC 3, Igloo, Fusion, and SmartFusion families. It also supports the G4 family. G4 means the SmartFusion2 and Igloo 2 families. And it supports the RTG4 family. And for this branch, there are no new enhancements and features for this branch. We only do a bug fixes with the service packs. The second branch is the 12.x software, which is the green bar. So we have the 12.0, 12.1, 12.2, and we recently released 12.3 software. So all the enhancements and the features we introduce in this 12.x software only. And this 12.x supports PolarFire, G4, and RTG4 families. So if, as mentioned in the previous slides, if you would like to work on the PolarFire, G4 and RTG4, you can use 12.x software because we actually have a lot of features which will be added up in the coming releases as well. If you are using older devices or older families, then please, we need to use this 12.9 or earlier releases. Here are a couple of key features of Libero 12.x releases. So there are a lot of features introduced with the 12.x. In terms of the SmartDesign canvas, we have introduced a new SmartDesign canvas, which is simple and intuitive. Visualization, it is very easy because all the inputs appears in the left-hand side and the outputs appears on the right-hand side of the canvas. And you can actually highlight any net or instance to easily navigate your design. It also supports in-place hierarchical expansion. I will show that in the demo. So we are now supporting tickle-based design for the SmartDesign, HDL plus, which means the custom HDL IP, and the core configuration. Using the UI, you can also export the tickle scripts from the UI. So this is the design flow. Libero design flow is comprehensive. You have the complete tool set from the design entry to the programming and debug. So using design entry, you actually create your design using the HDL flow or SmartDesign, which is nothing but a schematic entry. Once you create the design, you can do a functional simulation using simulation tools. We use ModelSim from Mentor, so that is integrated in Libero. Then you actually create generate a synthesis. So we use Synplify Pro. So until synthesis, you can actually use Libero tools. You can also use the third-party tools to generate a netlist model up to the synthesis stage. So that we call it as a front end. Starting from the place and route, you have to use a Libero software because it actually takes the resources available in the FPGA. So once you place your design and connects the routing, then you do the timing analysis using the smart time tool, and you do power analysis using smart power tools. So once you are satisfied, once the timing is met, and once you are okay with the power, the dynamic and static power of your design, then you need to program the FPGA using the Flash Pro or Flash Pro Express tools. Finally, you debug at the fabric level, at the hardware level, using the SmartDebug tool, which is the in-house Microchip developed tool. And you can also use the Identify Me from Synopsys to debug the FPGA fabric. So I will explain each and every stage of this design flow. Coming to the design entry, you have two methods of design entry. One is the HDL entry. The second one is the SmartDesign entry. Coming to the HDL entry, you have four components. One is the custom HDL. So using custom HDL, you can create your own design from scratch. So we support the VHDL language, Verilog HDL language, System Verilog, and mixed language entries. Once you create your design, if you want to create an IP from the custom HDL, you can actually create the custom HDL IP. So in the same project, if you want to use the same HDL code at multiple places in your top module, you can actually create a custom HDL IP, and using SmartDesign, you can place these IPs and you can connect all these IPs as a schematic entry. On the other hand, you have the HDL from MATLAB. So using MATLAB, it is actually easy to create the DSP designs. And once you create the DSP design using the HDL coder, it will generate a generic HDL code. That HDL code you can actually import using this HDL entry. So the fourth one is the HDL from the direct cores. So direct cores are nothing but the in-house, the Microchip in-house IP cores. For most of the IPs, we provide the HDL source code. You can actually generate the HDL source code from the IP, and you can use it, you can reuse it, you can actually modify it based on the requirement. But if you modify the HDL source code, Microchip will not give any technical support. So if you create the HDL flow, this is a simple buffer VHDL code. And if you want to create a custom IP from the HDL code in Libero, in design hierarchy, you can highlight on the HDL module, right click, and there is an option to create core from the HDL. So once you click on this option, it will create the custom IP. So let's see the demo. So I installed Libero 12.3. So once you click on that, Libero will open. Now I'll create a new design. If you would like to create a new project, you need to go to a new option. I actually created a project name as Lab1, and this is the project location. I would like to create HDL code. Next is device selection. I use PolarFire, and I'll choose MPF 300TS. I choose FCG484 package and -1 speed grade. So I have chosen the MPF 300TS-1 FCG484i device. So in this device selection page, you can see all the resources that are available for this particular device, like what are the flip-flops available, what are the user IOs available, and so on. You can also, if you know the part number, you can provide the complete part number here, then the tool will automatically highlight that part number for you. On the device setting page, For PolarFire, we have 1 volt and 1.05 volt. Currently selecting the 1 volt, and this is the default IO settings. So here I have the couple of IO standards. I can choose any one of these IO standard. If I select LVCMOS 1.8 volts, all the user IOs will be applied with this LVCMOS 1.8 volt. But if you would like to change any of these IOs, you can change it using the IO editor tool. I will actually show you the IO editor tool in the next lab. So here there is something called preserved pins for probes. PolarFire have 2 dedicated pins which are used to debug the FPGA design. So you can actually call any internal signal to this external probe pins and monitor the behavior of these signals using the scope. So if you don't want to use that, you can uncheck this option. When you uncheck this option, then those 2 pins can be used as a general purpose IOs. So I have a 2 input AND gate. I'll just open that. I don't have timing constraints, just keeping that tab. I have design hierarchy. So the entire design flow, which I explained in the presentation, the entire design flow is available here for you. And in the design hierarchy, whatever the HDL code we just imported, that will appear here. So once you build the hierarchy, then it will actually build the design. And if you write the HDL stimulus files, then that will be available in this tab. And we have plenty of IP cores. Depends on the segments. You can actually select any one of the IP cores like DSP IP cores and processor IP cores, macro libraries. You have a lot of bus interfaces. You have a lot of IP cores available here. So all these IP cores are developed by Microchip. It's an in-house IP cores. Okay, now it is actually asking me to set the root. So right click on the HDL module and set this module as root. Then it will actually show you the root module name here, which is _HDL. I would like to create a SmartDesign. I would like to create an IP core from the HDL. I can right click and I can select the create core from HDL. So till now, it actually shows as a VHD file. So when I click on the create core, it will be like the HDL plus file. When you create a core, you can also provide a bus interfaces to the IPs. Currently, I am not providing any bus interfaces, and the HDL custom HDL IP was created. So I'll actually show you how can we call that custom HDL to the SmartDesign, because SmartDesign actually supports this custom HDL into the SmartDesign canvas. So using the SmartDesign, you have multiple IPs. If you want to create an embedded design, you can actually create an embedded design using the 32-bit RISC-V IP, which is available as part of the Libero IP catalog. And using this IP catalog, you can actually use any of these IPs and create your own design using the SmartDesign canvas, which will actually save your time, because if you want to use FFT in your design, you have core FFT available in the catalog. You can directly drag and drop and you can set the parameters of the IP based on your requirement. And it also supports the companion core, which means the third-party IP cores, but it is not available as a default. If customer pay for the IP, so the partners will provide the CPC files, which is like an IP file. In Libero, you can actually import that third-party IP into the IP catalog. So I already explained about this custom HDL. When I show the demo, I'll actually call custom IP, and I also call the one of the core from the IP catalog and create a SmartDesign. So many of these points are covered in the previous slides. The one important point which I would like to highlight here is the in-place expansion of the SmartDesign within SmartDesign. So basically you have a plus mark here. So this is the top SmartDesign, one of the top SmartDesign block. So if you open this, if you click on this plus mark, inside that you have sub SmartDesign components. You can completely see the hierarchical view of all the sub SmartDesign components once you click on this plus mark. I will show that in the demo. So now I'm creating a SmartDesign block, create SmartDesign. I'll actually go to this design hierarchy. Now in this lab 2, so this is a smart design canvas. In this smart design canvas, I actually place this to input and gate, and I will also go to the IP catalog and select the AND gate macro. Now I'll promote these IOs to the top level module. So when I'm promoting the IOs to the top level modules, as I said, on the left hand side you have the inputs, and on the right hand side you have the outputs. So I can also modify the name of the I can also modify the name of the input port or output port. Now I generate the smart design. So I need to generate the component. Once I generate the component and build hierarchy, this lab to the smart design block, under that smart design block, the HDL plus is available under the lab 2 component. So if I create another, so if, for example, I want to create a 4 input AND gate using a 3 2 inputs AND gate, then I'll actually go to create. I'll go to the smart design and I'll actually call the lab 2. See this. I have this is the top component. Under that, I have 2 sub components, and I can actually call the another. I mean, I can actually instantiate the same 2 input AND gate and connect it. So the Y out to A underscore 0 to B, and I can promote all these IOs to the top module. So once I create it, then V2 has the lab 2 smart design block under the V2 top module. So if I create another smart design block, so now I want a single smart design component for the 4 input AND gate, then this is just an example. So just I want to show how you can expand and how the hierarchy of the smart design will be formed. So now this is like a 4 input AND gate. If you expand that, you have uh, lab 2 smart design component, and if you expand that, this is the hierarchical view of the top smart design component. So in that lab, basically I covered how to use the HDL plus module, which means the custom HDL, in multiple places in the same design. And I also discussed about how can you create a top level smart design component. Now let's see the enhanced constraints flow. So basically, if you this is the typical Libero SoC design flow. So now we completed the design entry flow, and now we are at the implementation part. So for the implementation, you have the synthesis, place and route, and timing verification. So for the implementation, you have to provide the constraints for the implementation block. So for synthesis, you can provide the the timing constraints, which is the derived constraints, which is like the user, which is like an SDC file. And you can also create FDC constraints, which is an FPGA design constraints from Synopsys. There are multiple attributes available in the FDC constraints document. So using that, you can actually create the FDC file and give it to the synthesis. At the place and route, so before placing and routing the design, you actually need to give the design constraints, which is again, it's a timing constraints, which is the .sdc file. And you also need to give IO constraints, floor plan constraints, and the NDC constraints, which is a netlist design constraints. So NDC is used at the compile stage. Basically, if you want to do this IO register compiling, you can actually create that in the NDC. Or if you want to preserve any one of the signal, if you feel that any one of the signal is missing when you are compiling the design, you can preserve that signals using the NDC files. PDC is nothing but a floor plan constraints. So you can actually lock the design placements using this PDC constraints. So IO constraints, as you know, it's an FPGA IO constraints. We will provide the FPGA pin names for your designs. At the verify timing, you actually provide a derived constraints, which is a .sdc file. So basically, in our PolarFire FPGA, for the embedded blocks like the SerDes, transceivers, or for the CCC block, or for the MSS block. So the tool actually creates the constraints for you. So we already developed the constraints or created constraints for you. Just there is an option to choose a derived constraints. Click on that, it will automatically create a derived constraints as SDC file for you. Most of the points I covered in the previous slides. The main thing is the enhanced constraints flow tool is a centralized tool used to apply all kind of constraints in a single UI. Like I mentioned in the previous slide, you can apply the IO constraints, timing constraints, chip planner constraints, the FDC, NDC, all kind of constraints you can apply at the single tool. And you can also verify the syntax in using this tool itself before even going to the implementation part. That actually saves the time for you. So instead of covering the constraints manager in the presentation, I will directly walk you through the Libero tool and show how the constraints are placed. To apply constraints, you need to go to the Manage Constraints UI. You have IO attributes used to provide IO constraints. You have timing tab. It is used to provide the timing constraints. You have the floor planner tab, which is used to provide the floor plan constraints, placement and routing constraints. And finally, you have the netlist attribute. So this is the netlist attribute tool. You can actually create an NDC or FDC files using this netlist attribute. So under IO attributes, you can provide the IO constraints either through a text file using a text file, or you can also create the IO constraints using the editor, IO editor. So if you see the IO text file, so which is the PDC file, you can actually set the IOs. This is the set IO. What is the port name? So this port name is nothing but this is used in your design under the entity. And for this port, it is assigning the FPGA pin name, and the pin name is H7. This is a fixed pin, and which is an input direction. So for each IO, it will provide the constraints like this. You can, if you know the syntax, you can write and update these PDC files. Or if you don't know the syntax, you can actually go to the editor, which is the UI mode, and using this IO editor, you can apply the IO constraints. Okay, so this is the IO editor tool. Okay, on the left hand side, you have the port view, you have the logical placement, logical view, and you have the nets that are used to create your to connect your design. You have nets view and you have regions view. On the right hand side, you have the port view. So this port view is used to display all the ports that you have used in your design under the entity section. Whatever the port names you have, that will be displayed here. And based on, and you can actually select that as input and output based on your HDL design. It will actually choose the input and output automatically. And as I said, the IO standard initially we set as LV-CMOS 1.8 volts. So it will show that as a default. For the SerDes lane, the tool will select the IO standard, so you don't need to select anything here. And these are the FPGA pins. So you actually select the FPGA pins based on your custom board. Once you select the FPGA pins, it will be locked. Based on the pin number, it will select the bank name automatically. On the pin view, you can actually see all the pin names, the FPGA pin numbers available for your selected FPGA. And if you see the lock option here, the lock column here, if you already assigned the designs, it will actually show you that these IOs are already assigned. See this, you already have a lock symbol here. So on the XCVR side, you have like a reference clock. This is the reference clock, and you have the TXPLL component. This is the TXPLL component, and you have the lane, the quad lane. Currently, I'm using the quad one. Each quad will have 4 lanes. Currently, for my design, I'm using the Q1 lane 1. So if you see this view, the top modules, I mean the top quad, I mean the quad 2 is in gray color because this reference clock cannot be cannot be used at this stage because the reference clocks coming from here cannot be connected to the Q1 quad. So that's the reason it is the gray. Similarly, you cannot use the bottom quad. For the other placements, you can actually change the placements from here to here and then any other places. You have similarly, you have memory view here, and you have package view where it will actually show you the unconnected pins, the unassigned pins, the fixed pins, like the ground and VCC pins. This is the floor plan view. I will talk about this floor plan view when I open the chip planner. In this IO attribute tab, if you create the constraints, if you create the IO PDC file, you can actually use the same IO constraints, and you can select any one of the devices available in this section. So you can actually migrate your device to a higher device if you're, for example, if you're currently working on 100T device, and if you feel that the logic elements which are available in 100K is not sufficient for you, so the same design you can actually import to 200G device. So you don't need to change the IO constraints here. That's an advantage actually. So on the timing tab, as I mentioned, you use the SDC files. SDC file format is used for the timing constraints. If you select this derive constraints, then the tool will automatically create constraints for the embedded blocks which are available in the FPGA. Like as I said, like SerDes or the PCI Express or MSS. The new option is used to create a new SDC file. So all these options are basically available in almost all the tabs. So the import, so if you already have the SDC file available, and if you would like to import that same SDC file in this project, then you can import. Now, if you don't want to import the SDC file, but you want to just link the SDC file which is available in the other location, you don't need to copy that SDC file to the current project, but you can just link it. If you know the syntax, you can actually write the constraints using SDC files. You can actually use the SDC file at the synthesis stage, or the place and route stage, or the timing verification stage. I have clock constraints, which is like 100 megahertz, and I applied to the user constraints .sdc file. And now on the second SDC file, I applied 200 megahertz as a clock constraint. So if we apply the same constraint and with the different values in the multiple SDC files, the tool will select the last SDC file which is available in this UI. So be careful when you are applying timing constraints. So on the floor plan constraints, this is used mainly the placement constraints. So all these options I already explained in the previous tab. You can actually view the placement constraints using chip planner, and you can actually modify it. You can lock the placements. You can create regions and lock the region. Based on my design, my logic is placed in this area. Now, if you expand the placement, you can see up to the gate level place. You can actually drag the placement to see placement. Using nets, I can actually view the connectivity of my design. So here is the placement, here is the IOs. So I can actually see the routing part from the IOs to the logics, and the logics to the IOs. So if you would like to create, regions on the log the regions, you can expand this macros, and in the floor plan view, you have create empty region, create inclusive region, and create exclusive regions. So using create empty region, so you are guiding Libero software to not to use this particular region to place the logic, because you will be using that area for any other glue logic in the future. So you are saving that region for the future use. And if you use the create inclusive, so what happens is, if the logic is placed at particular location and you create inclusive for that particular area, then you're basically guiding the tool, don't disturb the logic available in this particular region, but you can use this region for the routing resources. And when you actually create exclusive, then you are guiding the tool to not to use this exclusive region for the routing resources also. So I can create any one of the region at any one of the place. So then here I have something called a regions tab. Then the regions is created. I can rename this region. On the other hand, you have a netlist attribute. You can actually create the NDC file or the FDC file. So the compile netlist constraints is the NDC file, and the simplify from Synopsys simplify netlist constraints is the FDC file. So there is no editor or there is no tool to create the constraints. So if you see this NDC file, you are actually guiding the tool to preserve this instance name. So I covered the demo for the enhanced constraints flow. We use Synopsys tools for the synthesis. I already explained that in the previous slides. Using synthesis, you actually create an optimized gate level netlist. If you would like to create a state machine, you can also create a state machine using the Synplify tools. This Synplify tool will support the IEEE P1735 encryption standard. So if you encrypt your HDL code using this IEEE P1735E standard, the synthesis will allow you to synthesize the design. Coming to the timing analysis, so basically you already created the constraints using the constraints manager. So with Smart Time, you can perform the complete timing analysis of your design, and it will actually ensure that you meet all timing constraints. If you view the timing constraints UI, you can actually see the register to register paths, and here at the bottom side it will actually tell you how the slack distribution is in your design. So if the slack is positive, then the timings were met, and each path, each source pin and the sync pin, it will actually show you the delay and the slack value, arrival time, required time, setup value, and it will also show you the skew value. So if you double click on any one of this path, then it will actually open the SmartTime UI, where it actually shows the complete path from the clock to the data. And for that clock to data, it will actually show all the components. If you see here, it is from the clock source to the destination data. So from the clock to data, it will show all the components, and it will show the delay of each component, and it will calculate the arrival time for the path. And for the same path at the bottom, currently I didn't show the data required time calculation. At the bottom you have the data required time. So data required time minus data arrival time is a slack that should be positive. So and the other important feature of the smart time is you can actually cross probe the signals or the instance from the smart time tools to the chip planner, which is the floor planner tool. So using the power analysis, you will actually analyze the static and the dynamic power of your design. So the power analysis is very good in terms of visualization. So you can actually calculate the each and every component of your design. So in the FPGA, if it will calculate what is the dynamic power of the IOs, and what is the dynamic power of your logic, what is the dynamic power of your nets, what is the static power it consumed for the cores, for the memory. So each and every component it will actually show you, and there are multiple scenarios where you can actually apply, like the operating conditions you can change and see how the results are changing. So you can actually apply multiple scenarios and play with this smart power tool. Programming. So once the timing is met, once you're satisfied with the static and dynamic power of your design, then you finally program the FPGA using Flash Pro, or there are multiple methods to program the FPGA actually. So if you see the programming methods, you can program the FPGA using a Flash Pro hardware. You can also program the FPGA using external processor, and finally you can program the FPGA using the FPGA itself, because inside the FPGA there is something called a system controller. So that system controller acts as a spy master, and it will program the FPGA. So using the Flash Pro and the external processor, both the modes supports the JTAG and SPI programming. And as I said, inside the FPGA you have system controller that acts as a spy master. So basically, you are actually programming the FPGA using the external spy memory using this spy master. So in this, you have two modes. One is the auto mode. So auto means the FPGA is automatically programming the FPGA using the spy master, and the IAP application. So basically, it does the different kind of services for you. Like if you want to read the index of the external spy flash, then you can use the spy interface. You can actually read the base address of the bit streams. For that, you can use the IAP applications. And in auto, you have three different modes. One is auto programming. So which means if you have a blank FPGA and you are programming for the first time, so basically from the factory, you get a blank FPGA. Now you are programming for the first time from the external SPI flash. And if the external SPI flash has three different bit streams, version 1, version 2, and version 3, it will actually program the latest version that is available in the external flash, the highest version, which means the version 3 bit file. That is called auto programming. If you are programming for the first time and on the blank device, that is called auto programming. Now, second is auto update. So auto update will basically compare the bit file version available in the FPGA with the bit file versions available in the external SPI flash. For example, I have in my FPGA I have bit file version 2. Now on the external SPI flash I have bit file version 1, 2, and 3. Then what happens is on the power on reset, the FPGA will be programmed with the bit file version 3 from the external SPI flash. That is called auto update. On the auto recovery, so when you are programming the FPGA and while you are programming the FPGA, if there is an interrupt occurred and the FPGA went to an unknown state, then at that time this recovery will try to load the FPGA, the program the FPGA with the highest version of the bit file which is available in the external flash. So on the debug side, so we have an industry's best differentiated debug tool. You don't really need any FPGA resources to debug the FPGA fabric, to debug the memory available in the fabric, to debug the transceivers. You don't need any resources to basically debug the FPGA fabric. And you can actually change, you can actually change the probe points on the fly without recompiling the entire design, without recompiling the design itself. So basically you are saving your time because you're not recompiling the design, and you are saving the resources for your design because you don't need the FPGA resources to debug your design. So those are the two basic advantages of using the SmartDebug. In this training, I explained the design entry, the whole Libero SoC design flow from the design entry to the programming and debug.